Hello everyone. Let us begin with examples of open sets and closed sets today. Like I promised you guys last time, we are gonna present various examples like a set is open but not closed, closed but not open, and so on, these kind of situations. So let us first begin with few examples of uh, the sets which are both open and closed, of course with respect to some topology and a given set. So both open and closed. Now I think you know too, right? As you might have observed, what phi and x are both open and closed in any topological space. By the way, there is a name for such sets. What we call these sets? Clopen sets. Okay, I'm writing here in bracket. It means both closed and open. Second example, which we have already seen, is if you remember fourth space. So let X be an infinite set. And X naught in X be fixed. Consider X along with tau to be fourth space. I'm not defining it again since we have already done this, so I'm just specifying it. So what we had shown is singleton X is clopen for every X in X minus singleton X naught. You can see that singleton X naught is not clopen. Let me give you one more example which we have already done. Can you guess? Discrete space, right? So consider X along with the topology 2 to the power X. What's happening here? Every set is clopen, right? Every subset is clopen. Very good. Let me present you one more. So consider capital X is equals to R. We already know that we have two topologies here. Say first is phi n x and second is 2 to the power x. So what we know that every set okay, in topology, so basically okay, what we know that in X along with tau 1 and X along with tau 2, open sets are also closed and vice versa, right? Because every, okay, all open sets I should write here. So because every open set is closed, right? Because in tau 1 you have just two open sets, phi and x. What is the complement of phi? that is X, which is in topology, so it means V is closed, right? Similarly, X is also global, and in discrete space, of course, we have mentioned above, right? So I have a question from you guys. Does there exist a topology on R other than discrete or indiscrete such that every open set is closed and vice versa? What I mean by vice versa, and every closed set is open. So other than these two topologies, do you have any other topology? So that is what my question to you guys is. I want you to stop the video and think over it for a moment of time, or think over it. Try to answer this question, and once you get your answer, you can continue watching video. Okay. So let me present you a solution for this. So answer is yes. There will be many. Okay. So let me define one of them, or let me write in general. So choose capital A belonging to 2 to the power x such that A is non-empty and as well as A is not equal to x. Okay? Define tau to be phi along with A complement along with x. What I want to observe you guys is, note that tau is a topology on R which serves our purpose. Okay, so I think these examples are sufficient for the open sets, the sets which are both closed and open. We will be encountering many of them later on also. So let me proceed with an example of or the examples of the sets which are open but not closed. So let me give you first example of this. See, there can be many examples. You might have guessed many in, I think, metric spaces, right? So let me give you something, different. Let x is equals to r. consider the cofinite space. So what I mean by this, I am considering R along with cofinite topology. Please recall that cofinite topology is a topology which has empty set and all sets whose complement is finite. So those are the open sets, right? So now, is it fine? Yeah. So let us take some open set. So let U is equals to R minus 1, 2. Note that, guys, this is an open set. R COF. So what I mean by R suffix COF? R along with cofinite topology. Why? Because its complement is finite. Now, is U closed? So let us see what its complement is. So X minus U is, what is our X? X is R. One comma 2. And see, what is the complement of 1, 2? It's an infinite set, right? So, which is not open, which 1, 2 R, because this is a finite set of R and its complement would be infinite set. So this cannot be an open set in R along with cofinite topology. So this implies, what it implies? U is not closed. Why? Because if it is closed, then its complement has to be open, right? And if its complement is open, the complement of its complement should be a finite set, which is clearly not the case here, right? So let me just end up with this example only. You can see various examples in metric spaces as I have said to you. Okay. Now, closed set but not open. Okay, guys? So let me again consider the same space. So consider, I'm just giving you one example only. Consider, because like how I am constructing, I haven't written it anywhere. If I have better technology, then I would have been, recording my video also, but unfortunately I don't have money for that, as well as like the features, because that needs some software or some premium subscriptions to record your video also along with this. So I'm just doing it whatever comes to my mind. So like that you should also construct various examples. Okay, so consider R along with cofinite topology, basically this notation like we have used. Okay, now or yeah, this is fine. Consider f is equals to, say, -1, 0, 1. Okay, what I claim is f F is closed in RCOF. Why? Because if you take the complement of this and its complement, then this is a finite set. So basically X minus F is open, so F is closed by definition. And clearly X minus F what's the cardinality of this set? It's infinite set, right? So this implies F is not open. Where? In R along with cofinite topology. So this is an example. Now what we are left with? We have given example of sets which are both open and closed. One is closed, another is open. One is open, another is closed. The next thing is neither closed nor open, right? So neither closed nor open. So let me again give you an example of this, only one example of this. You can similarly construct more. So consider R along with, I hope now you have guessed the name of the topology tau suffix COC, that is co-countable topology. What I have asked you to think about with co-countable topology. So we will denote it by R suffix COC or any space suffix COC. You can use this notation if you want, but you have to specify wherever you are using this, because this is not something very standard notation, right? So what is this topology? If you want me to recall, it is this topology comes with empty set in its definition, and it has all sets whose complement is what? Countable. Okay. So let me give you an example of the set which is neither closed nor open. Let U is equals to open interval 0, 1. Guys, what is U? Is it countable? No. So which is uncountable or not countable. What is R minus U? This is also, okay, let us write it minus infinity to 0 union 1 to infinity. It is also not countable. So you see what you're getting from here. U and R minus U are not open in R along with co-countable topology. So this implies U is neither open nor closed. Right? So this is an example. You can construct similarly many examples. Why in this topology only? We have seen other topological spaces also, right? Ford topology, uh, cofinite topology. You may construct examples there. So my advice is to you guys is to construct at least 3-4 examples of each type. It will not something very trivial. By trivial I mean whatever you already know. Try to construct some new examples. Okay, so let us have two very standard things, examples of two very standard things. We have learned that finite intersection of open set is open. What about the other case, right? So in general, a non-finite intersection of open set need not be open. See, I think you guys know that this convergence 1 upon n goes to 0 is probably one of the most important convergence we have ever seen. So using that only, let me produce example. Consider the real line R. What do you mean by real line R? I mean R along with Euclidean metric. Or you also call it usual metric if I am not wrong. The distance between 2 points, that's all. So that's what you call this thing is real line. So whenever it is written somewhere, let R be the real line. So which topology it has, you should know. So real line term comes with this topology. Okay, of course you haven't learned these things in 12th class. How you would have, because you don't know the concept of topology, but you might have used the word till 12th class many times, real line. But that is what real line means. It's not just the real numbers. It comes with the usual topology, the Euclidean topology. Okay, fine. Now, so let me give you an example of this. So define un is equals to minus 1 upon n to n, open interval. I hope you know, nothing to show here. This is clearly open in R for every n in n, right? Let us see what is the intersection. So choose x in intersection un n in n. N is varying, right, from 1 to infinity. You may plot this and you may get the idea what's gonna happen. So minus 1, 1, minus half, half, like this. So you see these intervals are nested and they are shrinking towards the point. Which point you know, right? So let x belongs to intersection un n in n. So what it means? X is in un for every n in n. What it means? Minus 1 upon n is strictly less than x, is strictly less than 1 upon n for every n in n. Now, like I said, 1 upon n converging to 0 is a very crucial sequence. So what you will get, guys, by your which theorem? Squeeze theorem or sandwich theorem. You will have 0 less than equal x less than equal 0. So this implies x has to be 0. So if you have any point in this intersection, it has to be 0. So this implies intersection un n in n is singleton 0, right? So you know what is r minus 0, the complement of this? The union of these two open intervals. This is clearly open in R, right? Of course, we will be, you see, using the things which we already know from metric spaces. You can apply any result whenever you have a metric space. But mostly the things what I will be doing today, I will not use any result from the metric space to show something is closed or open. If I am taking a metric space, I will be using my definition only, the usual open set and closed set definition. Okay, so this is singleton 0. Is this open? No, right? This is not an open set in metric space R along with Euclidean metric. So which is not open. Okay, good. Why? Like the logic how you take. You have to have an open ball around 0 to be wholly inside this singleton 0 if it is open. But you know that is not possible, right? I'm not gonna prove this. So I hope this is clear. Similarly, in general, arbitrary union of closed sets is not closed. Of course, finite is, but not the arbitrary one. So this I am leaving for you guys. Again, you have to use somehow this convergence of the sequence 1 upon n, and you will get your answer in the real line only. So please do it. Good. Now let me okay. Yes, let me take one more example at least. So consider the set. Okay. Consider R square along with Euclidean topology. What I mean by it? Of course, with the Euclidean metric, the usual distance in R2. So, show that. Number one. Let us take something. Okay. X comma y such that x is equals to 2y and y strictly between 0 and 1. is neither open nor closed. So let me do this. It might be very trivial for you, but I want to do it by the definition of open set and closed set. Like closed set, what is closed set for me? Whose complement is open. So that's what I want to use, and I want to to show you how to write these things precisely. So let me just have this, and you can construct similar examples and check if it is open, close, or one of them or none of them. So let me begin. Okay, so let us denote this set by, say, capital A. Capital A is not open. Let us see why. Okay, so let's first plot this. So this is, say, 0. This is, say, 1. And this is, say, 2. So you see, this is this line. 0 is not included, 1 is not included, right? So this thing. Now, what you want to show here is A is not open. As you might have clearly observed, if you take any point here, say, and you take any ball around it, you know how the Euclidean ball looks like. It's like a open ball. It's like a disk, open disk, right? So you see, if you take any ball, it has what? It cannot be wholly inside the set A, right? So you see that this set A is not open, right? So let us proceed. So take any x strictly lying between 0 and 2, then what is our claim? For any r bigger than 0, the ball centered at the point x comma y, right? What is y? X by 2. Along with r is not sitting inside where? The set A. I hope this is very clear to you, but still we should have a point, right, which is inside this ball, right? So now, how to choose that? So like there are various ways or to choose a point, right? So how you are gonna choose that? See, it's this is nothing but this is an open disk. So choose any point which doesn't lie on this line. So choose any point x comma y in B x comma x by 2, this is my center and radius is r, such that it doesn't lie on that line. X is not equal to 2y. You will have plenty of points, right? You can also take in particular, if you want to take any value, you can take some value around the point, no issues. So then what is our claim? So okay, a comma b, let me write a comma b because x I have already used. this implies A comma B does not belongs to A. So this is the reason. So I hope you get it. Like, I know you know it, but if you have to be precise, right? You should know also how to write it. Okay? Now, let us do the other thing. A is not closed. So what do you have to show equivalently? Equivalently, we need to show what we need to show? R2 minus A is not open, because if it is open, then you can see that what you can see? You can see that this will this A would be closed if R2 minus A is open. So let us again plot it. So now except you have, okay, this is my A, and let me, apart from that, including this point, everything is this R2 minus A, right? Apart from that line, including this point. So yeah, so I hope you, of course, you know what it is. So apart from this line, let me do it with red color. No, this is a very bad plot, I know. So let me remove it. Let me replot it. I think I don't need to show you what is R2 minus A. So apart from this line, this thing, apart from this purple thing, including these two endpoints, that is my R2 minus A. So what our claim is, R2 minus A is not closed. So if you take this point 0, 2, 1. So if you take 2, 1 and you take any ball around this 2, 1, is it wholly inside? Is it wholly inside R2 minus A? No, right? So that is the precisely idea. So choose 2, 1 in R2 minus A. Clearly, for any R bigger than 0, the ball centered at 2, 1 with radius R is not sitting inside R2 minus A. Now how you should proceed this point? So basically, right, there is a point which is not in this but in R2 minus A. So let alpha comma beta is equals to, let alpha comma beta is equals to the point on the boundary of ball. Okay, basically x comma y such that x minus 2 whole square plus y minus 1 whole square is less than r square, intersection the line, what we have, this purple line, the set A. So basically, what is my alpha comma beta? This is my alpha comma beta, this point. Now, let A comma B be the midpoint. Nothing special about midpoint, you can take any point. Midpoint of line segment joining alpha comma beta and 2 comma 1. So where it would be? It would be somewhere here, right? This is your A comma B, in between, right? This is if you want to magnify it. So if you want to magnify this thing, so what's happening here? So you have this thing, alpha comma beta, some ball is here, yeah, of radius r, and okay, so this is not alpha comma beta, the ball is like that, some ball you have. Now this is alpha comma beta, and this is your 2 comma 1, this point, and here you have this A comma B, which is midpoint of this. So you can clearly see what A comma B belongs to the ball, but A comma B does not belongs to R2 minus A. So you see, I have specifically produced existence of a point, right? That's what I mean by writing properly. Definitely you have an idea. Definitely you have an idea, but that idea you should, you should always able to write. So let me end by this example, and you can construct similar examples, and what you can try to write it down properly. So what was the conclusion? So this implies R2 minus A is not open, which further implies A is not closed. So of course you can pictorially got everything, but you should be able to properly write it also, whatever you are thinking. That was one of the aim of this session, to make you guys, if you don't know how to write things, because like I said, you can only understand a concept in mathematics if you are able to write it down. Otherwise your understanding is incomplete. With this, let me end this session. Thank you very much. Let's meet in coming session, and we will be discussing about some sort of comparisons of topology in the coming session. Thank you very much.